So it's recording now. So we have in this example 7.1, the air leakage into condenser operating in conjunction with the steam turbine is estimated at 38 kilogram per hour. So this means we have the air is leaking into the condenser at the rate of 38 kilogram per hour. This means this is M dot A, mass flow rate of air into the condenser, equal 38 kilogram per hour. So we put M dot A like in here. So we transfer actually any question we should put the data in symbol and units, value and units like this. So M dot A equal 38 kilogram per hour. Then we have the vacuum near the outlet to the air pump is 72.4 centimeter. So it means this is the gauge pressure, which is the vacuum pressure, is 72.4 centimeter. So we put PC, pressure in the condenser, equals 72.4 centimeter, Hg mercury, vacuum. So this is the vacuum pressure, it means gauge pressure. Barometer, 76 centimeter, it means the atmospheric pressure, PATM, atmospheric pressure, 76 centimeter, Hg mercury. Again, this is at the sea level, like in here in Jubail. So at sea level, this is the pressure, which is 76 centimeter Hg in the manometer. And the temperature at this point, it means at the inlet to the air pump, it is 20 degrees centigrade. Determine, we need to find the minimum capacity of the air pump. Capacity of the air pump, which is the V dot A, capital V dot A, it means volumetric flow rate of air. Volumetric flow rate of air. We have the mass flow rate of air. We need to find the volumetric flow rate of air. And the second question is the mass of vapor extracted with the air per minute. It means we need to find the mass flow rate of steam per minute, which is kilogram per minute, which is leaving with air. So the steam leaving with air through the pump from the condenser to the outside. So M dot S is required to find in kilogram per minute as per the question. Also given the vapor pressure corresponding to 20 degrees centigrade. So this is PS, partial pressure of steam in the mixture of air and steam passing through the air pump. So PS, partial pressure, equals 0.0226 bar, which you can find also this one. If it's not given, you can find it from the steam table, saturated steam table. At T saturation 20 degrees, you find the P saturation 0.0226 because we have saturation here. So we can get the PS in here, partial pressure of steam. So you can get it also from the steam table at saturation temperature 20 degrees centigrade. So this is PS, partial pressure of steam. Then we have the specific volume, small v specific volume for the steam. So Vs equal 60.86 meter cube per kilogram. So these are the given. We'll try to find out the capacity of the air pump or the volumetric airflow rate of pump, which is V dot A, and the mass flow rate of steam leaving the condenser through the pump. Okay, let's look into the solution. Right. So we have the now to find the capacity of the air pump, V dot A. So this is the V dot A should be there. We can find it from the equation of state. Equation of state PV equal MRT. From thermodynamics, you have the relation for gases. PV equal MRT. So V and M can be volumetric flow rate and mass flow rate instead of volume only and mass. Because we have volumetric, we have mass flow rate, so we can get the volume flow rate, volumetric flow rate. Now the equation PA V dot A equal M dot A RT. RT for air. R is the gas constant for air, which is 287, which is a constant, 287 joule per kilogram degrees Kelvin. And T is the temperature of the air, which is given 20 degrees centigrade. We have to add 273 to make it in a Kelvin. So the R is, we know R, we know T. Mass flow rate of air is given. So we need to find partial pressure of air, PA, so we can calculate V dot A, which is the capacity of the air pump. Now, to find the partial pressure of air, we have to find the this from the relation PC equal PA plus PS, because we have a mixture in the pump of air and saturated steam. So PC, pressure and the condenser, absolute pressure in the condenser equal the partial pressure of air plus partial pressure of steam. This is Dalton law. When you have mixture of gases, the total pressure will be equal to the sum of the partial pressure of the gases. In this case, we have air and we have steam. So, or we can put PA equal PC minus PS. PS already, as I said, you can take it from steam table, which is already given here in the question, and we can find it from steam table at the temperature, saturation temperature 20 degrees centigrade. So PS, we know it. So we need to find PC, the absolute pressure in the condenser, not the gauge pressure. So we have to find the absolute, because these are the absolute values. So PC, absolute pressure, equal to the atmospheric pressure or barometer, which is 76 given, minus the gauge pressure, vacuum pressure, which is 72.4 centimeter, equal 3.6 centimeter Hg mercury. So this is the absolute pressure in the condenser in centimeter mercury. Now to change it to bar, so we divide by 76 and we multiply by 1.013 bar. Why we have this? Because this is 76 centimeter mercury equivalent to 1.013 bar. From where we get this relation? From the relation P equal rho GH. Pressure in Pascal equal rho density in kilogram per meter cubed, which is for mercury, it is 13,600 times the gravity G 9.81 meter per second square times the height, which is, if it is 76 centimeter, it means 0.76 meter. We have to change it to meter in the equation rho GH. Then we get the value 1.01300 actually in Pascal. To change it to bar, we multiply by 10 to the minus 5. It becomes 1.013 bar. So that's how we find the relation between 76 centimeter mercury and 1.013 bar. So this is the atmospheric pressure. So always this is quickly, you can do the change from centimeter mercury to bar by dividing by the 76 centimeter or 760 millimeter if this is in millimeter, times 1.013, then this will change the partial pressure of in the condenser into a bar, which is equal 0.048 bar. This is the absolute pressure in the condenser. So we know PC and we know PS, so we can find the partial pressure of air, which is the difference, and we get it, 0.0254 bar. Now we know the partial pressure, then we use the equation of state, PA V dot A V dot A equal M dot A R T. R and T are given, as I said, as constant, and BT temperature of the air, which is given at the inlet to the pump, to the air pump. Now, partial pressure is in bar. We have to multiply by 10 to the power 5 to change it to Pascal again, because this should be in Pascal here, if R is in Joule per kilogram degrees Kelvin. So times V dot A, this is not small v, you can just change it better to put it capital V dot A, which is the capacity of the air pump, equal to the mass flow rate of air, which is given 38 kilogram per hour, times R, the constant 287 Joule per kilogram degrees Kelvin, times the temperature in Kelvin, 273 plus 20. We add 273 to change from degrees centigrade to Kelvin. Then we get V dot A. So this will give us V dot A equal 1254.3 meter cube per hour. We can change the unit if we need to, because it's required kilogram per minute in the 4MS. So we change it to meter cube per minute by dividing by 60. We get from meter cube per hour to meter cube per minute, 20.9. So this is now we calculated the V dot A, which is the capacity of the air pump, or the volumetric air flow rate of in the pump, in the air pump. The second part is the mass flow rate of steam. How to find the mass flow rate of steam passing through the pump, the air pump. This is, we can get it from the, also in thermodynamics, you have seen that the capital V dot A is equal mass flow rate of steam, M dot S, multiplied by specific volume of steam, Vs. So mass times specific volume, this will give us the total volume. In this case, it is actually volumetric flow rate, so obviously the mass will be mass flow rate. So M dot S equal V dot S, V capital dot S over small vs, which is the specific volume of steam. Specific volume of steam is given already in the question, 60.86 meter cube per kilogram. V dot A we already calculated there. So now, what's the relation between V dot S and V dot A? So we have V dot A. V dot A and V dot S is the same. Why? Because it's mixture, right? Because the air and the steam are mixed together in the pump, right? So they have the same volume. So V dot S and V dot A are equal. So M dot S equal V dot A, or which is equal to V dot S over V small vs, with specific volume. Then this will give us the mass flow rate of steam. Any question? Anyone has any point didn't understand? Anyway, you need to solve it again. After we finish, you try on your own. If anything you didn't understand, you can also ask again. Right, we'll move now to the second question. Right, example 7.2. Now, in this question, you will see that most of the equations will be similar now what we have used. So we have a closed vessel of 0.68 meter cubed capacity. It means this is the volume of the vessel. This vessel simply represents the condenser. So the volume of the condenser or the closed vessel is 0.68 meter cubed. So we can put V equal 0.68 meter cubed. Contains saturated water vapor. So it means saturated steam and air at a temperature of 40.5. So we'll call it T1 equal 40.5, temperature of the mixture of air and steam in the condenser. And pressure of 0.11 bar, so we call it P1 in the condenser, 0.11 bar, and T1 40.5. Due to the air leakage into vessel, now after air leaked into the condenser, the pressure rises to 0.22 bar. So the pressure P2 becomes P2, rises from P1 to P2, 0.22 bar. And the temperature falls, decreases into 36.8 degrees centigrade. So we call them P2 and T2. This is after the air leakage. The question is to calculate the mass of air which has leaked in. So we need to find how much air leaked into the condenser, mass of air, MA. Here no flow rate because already it's only volume. We don't have as flow rate. So how to find the mass of air leaked? We find the mass of mass of air leaked, which is the difference between the air in the second condition minus the air in the first condition. So the mass of air in this MA2 in the second condition after the air leaked, we calculate the mass of air. And in the previous condition, P1 at P1 T1, we calculate MA1, mass of air at condition 1. So MA2 minus MA1, this will give us actually the mass of air which leaked in, right? So, and the mass of air, how to find mass of air in each condition? Again, we use the equation of state, PV equal MRT, PV equal MRT. So PA, VA equal to mass MA RT, which is R and T for the air. So we'll go to the solution down. Now, so M dot A equal M dot A2 minus M dot A1. Sorry, not M dot here because no flow rate, it's only mass. So it's mass, no dot there. MA equal MA2 minus MA1. It can be, of course, a flow rate if the volume is changing with the time. If it's given in, it's only given volume, not volumetric flow rate. Right, so how to find MA1 and MA2? At T1, we find PS1, saturated pressure, partial pressure of steam at T1. So from steam table at T1, we can find the partial pressure of steam PS1, 0.0755 bar. This is from steam table. So this is partial pressure of steam at T1. Now PA1 is equal to P1 minus PS1 because P in the condenser P1 equal to PA plus PS, right? Some Dalton law. So PA equal P1 minus PS1. We know P1, we know PS, we found PS1 from steam tables, then we calculate PA1. Now PA1, we know it, then we can find the MA1, mass of air in condition 1. PA1, VA, which is the volume of air, over the RT1. V air is the same as the volume of the cylinder. For steam and for air, it will be the same volume. So this is V of the cylinder which is given, or the vessel. And R constant and P1 we know it, PA1 we found it, so we can calculate MA1. Now in this equation we have to make sure PA we use the Pascal, changing bar to Pascal times 10 to the power 5. Volume is in meter cubed given. R 287 in joule, it should be in joule if we use Pascal here. If you use kilopascal, you can use kilojoule here. It becomes 0.287 if you use kilopascal. It will be the same thing. If you use Pascal and joule, or kilopascal and kilojoule will be the same thing. So times the temperature in Kelvin. We add 273 to the degrees centigrade temperature. We found Ma 1.026 kilogram. Similar to PS2. At T2 we find PS2 from steam table again, and then we use PA2 equal P2 minus PS2. We find PA2, and again we use the equation of state Ma2 equal Pa2V over RT2. We get the Ma2, then the mass of air is the difference, Ma2 minus Ma1, and you find the difference. So as you can see, this is similar to what we have done before. The principle is the same. Any question? All right. Now we'll move to the third question. So this is the exercise number 10. A steam turbine uses 45,360 kilograms of steam per hour, which it exhausts at a dryness of 0.9. It means dryness fraction 0.9 into a condenser. So this is the dryness fraction X at the inlet to the condenser, which is the same leaving the turbine. So this is the mass flow rate of steam, m dot s. We write it down in symbols. M dot s equal 45,360 kilogram per hour. X, if you like, you can call it X2, which is outlet from the turbine, which is given 0.9 dryness fraction. With the barometer at 760 millimeter of Hg mercury, so barometer, it means atmospheric pressure. So PATM, atmosphere, equals 760 millimeter mercury, or 76 centimeter, the same. We have, and the vacuum at the air pump suction, inlet to the air pump, is given 718.8 millimeter mercury as well. So this is the gauge pressure, vacuum pressure in the condenser at the inlet to the air pump. And the temperature of the air and the steam leaving the condenser through the air pump is also given. The temperature is given 32 degrees centigrade. Also, the air leaked or leakage is estimated at 1 kilogram per 1,000 kilogram of steam. So it's given also, so it means mass of air for m dot A, because here we have mass flow rate, m dot A over m dot S equal 1 over 1,000. So you can put the m dot A over m dot S equal 1 over 1,000 given. So for every 1,000 kilogram of steam, we have 1 kilogram of air leaking. Right? So then we can calculate m dot A, because m dot S we have it already. Now the question is, estimate the net capacity of the air pump. It means calculating or determining the capacity of the air pump, which is V dot A. the one we calculated in example number 1. V dot A equal how much? The volumetric air flow rate in the air pump or the capacity of the air pump, V dot A. Also, we need to calculate the quantity and the quantity of circulating water. It means mass flow rate of water, cooling water, right? So water is the cooling water. Circulating water in the condenser, usually we have the cooling water. So M dot W equal how much? If the temperature rise is limited to 15 degrees centigrade. So this is delta TW, change in temperature of water. It means T hot, where the cooling water enters cold water, leaves hot water. So the output temperature T hot minus T cold equal 15 degrees centigrade. So this delta TW of the cooling water in the condenser, which is separate, of course, from the steam. This water is only to condensate the steam, so it's separate cycle, as you remember. So we need to find V dot A, volumetric flow rate of air, or the capacity of the air pump. And also we need to calculate the mass flow rate of water, of cooling water, to condensate the steam. So this is the TS diagram. TS diagram, we can see the 1, 2 is the expansion in the turbine, isentropic expansion in turbine. 2, 3 is the condensation at constant pressure in the condenser. And 3, 4 isentropic compression in the pump. And 4, 1 adding the heat in the boiler. So to find the capacity V dot A of the air pump, we use the same equation which we did before. PA V dot A equal M dot A RT, equation of state. So we need to find the partial pressure of air. Mass flow rate of air we can calculate from the relation M dot A over M dot S equal 1/1000. So this means we have both of the M dot S, we know it, so we can calculate M dot A, 45.36 kilogram per hour. R, the gas constant for air, equal 287 joule per kilogram degrees Kelvin, as we have mentioned it before. The temperature is given, which is 32 degrees centigrade. We have to use it in Kelvin. We are 273, right? So we know T, we know R, we know M dot A. We need to find PA before we can calculate V dot A, the capacity of the air pump. How to find the partial pressure of air? The same as we did before. So we have to find the absolute pressure in the condenser, and we have to find the partial pressure of steam, and then we can calculate the partial pressure of air. So in the condenser, the absolute pressure in the condenser, P in the condenser, equal barometer minus vacuum. It means the atmospheric pressure minus the vacuum pressure or gauge pressure. 76 minus 71.88, which is the gauge pressure, the vacuum pressure. This will give us the absolute pressure in the condenser. Then we can change it to a bar. We divide by 76 times 1.013. This will change the pressure in the condenser, absolute pressure in the condenser, into bar, 0.0549. PS, partial pressure of steam, we can find it from steam table at 32, because temperature is given, saturation temperature 32 degrees centigrade, we can find PS. So PS equal at 32 degrees centigrade from steam table, we can find it equal 0.04754 bar. Now we find PA, partial pressure of A, which is P minus PS, we get 0.00736 bar. Then we can use V dot A equal MRT over V. Yes, you have a question? Okay, so the mass flow rate of steam we found. The R, we know it to 87 joule per kilogram degrees Kelvin. This is temperature in Kelvin. The pressure, we have to make you to change the unit from bar to Pascal by multiplying by 10 to the power 5. So this will give us actually meter cube per hour, because the mass flow rate is given in kilogram per hour. So the volume flow rate will be meter cube per hour. And you can change it to minute by dividing by 60. It will be meter cube per minute, which is 89.91. Any questions so far? Then we move to the further to the find the second part, which is the mass flow rate of cooling water. Right. Now you look into this figure here, simple sketch for the condenser. From the energy balance in the condenser, we can find the mass flow rate of cooling water. Cooling water, as you remember, so we have the cooling water will enter cold water. It will be through a coil pipe, and it will leave as hot water. So we have a pipe coming in and leaving out as hot water, entering cold water, leaving hot water. So delta T is given for water, which is 15 degrees centigrade, delta TW. So the heat gained by the water, cooling water, equal mass flow rate of water, m dot W times Cp, specific heat of water, which is 4.187, this is a constant as well, kilojoule per kilogram degrees Kelvin, times delta T, which is given 15. So this here, m dot W, Cp, delta T, this is the energy gained by the cooling water. This is equal to the energy lost by the steam. So steam entering the condenser and leaving the condenser. So energy entering minus energy leaving in the condenser, this will be the heat lost by the steam. So which is equal m dot S H2 enthalpy at inlet minus H3, which is the at the outlet from the condenser. Now, how to find H2? M dot S is given, how to find H2 and how to find H3 in here, which is difference H3 minus H2 minus H3. H2, we know the dryness fraction, which is the at the inlet to the condenser, which is, we called it X2 or X. So from X, we can find actually the H, the enthalpy of the steam at the inlet to the condenser. From the relation H equal HF plus X HFG. You remember this relation, right? So H equal HF plus X HFG. This is if you have saturated steam. So this is, of course, H2, it will be equal to HF2, which is at the pressure at 2, which is the pressure in the condenser, right? Which we calculated the absolute pressure in the condenser, we found already there, 0.0549. So it means H2, we can find it at pressure in the condenser, absolute pressure. And we find HF and HFG at the pressure of the condenser. 0.0549 approximately equals 0.055. So we can find out the HF, it will be 145 kilojoule per kilogram. And HFG is 2419 from steam table, from saturated steam table. This is 0.90x. So HF plus X HFG, this is the H2 or the enthalpy at the inlet to the condenser, minus the enthalpy of the steam leaving the condenser. Here we have the condensate at the temperature. We know the temperature, which is given 32 degrees centigrade is given. So at this temperature, we can find HF, So H3 is the saturated water leaving. So the steam become a water here, becomes water, and so H leaving, it is HF at the saturation temperature 32 degrees centigrade, because we know the temperature. So the enthalpy will be the saturation temperature, saturation, the enthalpy of the water saturated water leaving the condenser. It means HF at the temperature 32 degrees centigrade, which is the leaving temperature of the water. So from steam table, again, we can find HF at 32 degrees centigrade, which is 134 kilojoule per kilogram. Then we can find MW from this relation, which is very high, as you can see, very high number, 1,580,323.5 kilogram per hour, or 1,580 ton, 0.3235 per hour. So very high flow rate of cooling water. Any question? So I want you to solve them again now. So go through it again. So download this file from the course content from Blackboard and try to solve these three exercises without looking for the solution, right? Make sure you practice until you make sure you can solve these exercises. So this, as I said, these exercises for the theory only, not for the lab. These are supporting the theory. So you will be asking the theory about this. In the lab, you will be doing the same as the experiments only, as the lab reports. So your exam will be similar to the lab reports. Let me